So for earthquakes, we're going to break this up into two separate parts. First of all, this idea of rock deformation. To deform means you change shape, and we know what rocks are. Rocks aren't very squeezable. They're not like a sponge. They don't change shape. They're not compressible. But when we have two huge tectonic plates moving towards one another, this area right there where they come together, those rocks get squeezed and changed or deformed under pressure. Well, what happens eventually is the rocks give way to that pressure and they unsqueeze. That idea of the unsqueezing and then the releasing of the energy, which is then transmitted through the ground, is what an earthquake is. An earthquake is just the release of energy from when rocks are squeezed together and then they eventually snapped. The idea of rock deformation is the first idea that we have to understand in order to talk about earthquakes, and that is the bending or squeezing together of rocks where plates interact, and that releases energy. Now, the epicenter of the focus is this point right here. It's that actual point under the ground where the rocks are being squeezed together and then snapping. The epicenter here is the term that we tend to hear about on the news. The epicenter is the part on the surface directly over the location where the rocks have actually snapped. And the energy gets transmitted in all directions when those rocks snap. The first people to feel about it are the people at the epicenter because they are closest to where the actual earthquake is happening. So we need to clear something up here. The epicenter, which is what you hear in the news, is not where the earthquake happens. Earthquakes happen here, underground. That's the focus. That's the place where the rocks are being snapped and release the energy. The epicenter is the point above the ground where you first feel that release of energy. Now, when the faults move, there are actually two types of movements. You get one that's called an uplifted fault, where basically one fault is being pushed up and other fault is being pushed down, or you can get two faults sliding past one another. In either case, the rocks right in that area are going to be deformed. They're going to be squeezed. They're going to be pushed. They're going to be snapped. And that's where we're going to have earthquakes. You can see offset or displaced faults, transformed fault movement in this picture here. Orange groves in Southern California, they were planted in nice, neat rows, but when the ground has actually slid past one another, you see that displacement. Here's a freshly plowed field where you can see the same thing. It had an earthquake happen and some of the land moved that way, some of the land moved this way, and you can see where that movement took place. In 1906 in San Francisco, a very famous big earthquake, there was a fence over here that was displaced about 6 feet. That's how much the ground moved. And here you can see it in this road where part of the road was moved one side versus the other. As opposed to uplifting, where you can see where the ground was actually lifted up. Same thing here. Here's a concrete drainage channel. You can see how much the fault movement lifted up one side versus the other. So here's Wallace Creek coming downhill, and we would expect the creek to run that way and go straight out to the lowest point, but it doesn't. You'll notice right here, the creek takes a hard right-hand turn before going straight to the lowest point. And that's because this side of the creek that I'm standing on is on one side of the San Andreas Fault, and that part of the creek over there is on the other. And we're having a movement at the fault. The land I'm standing on is now moving this direction. That part of the creek over there is moving the opposite direction. So the creek has this hard turn in it because one side of the creek is moving one direction and the other side is moving the other. And this is how we actually know how much and how fast the San Andreas Fault is moving. We can come out and look at, well, how far has this creek been curved? And that'll tell us an age and a how long and a how fast the land is moving, which makes Wallace Creek one of the most studied places here on the San Andreas Fault. So let's talk about fault creep. And if you remember from our discussion of erosion, we know that creep is that slow movement of sediments. Well, fault creep is the same thing. It's the slow motion of faults past each other. It's not a case where the faults get snagged on each other and then they snap and move a lot at one time. They're just kind of slowly sliding past one another. And that's what we have happening here. I'm in Parkfield, California. You can see the sign behind me. I'm standing on the San Andreas Fault.
I'm actually in the North American plate right here, but on the other side of this bridge behind me is the Pacific plate. And these two faults are constantly, slowly moving different directions. Well, that means this bridge right here, where this side of the bridge is on the North American plate and that side of the bridge is on the Pacific plate, are actually moving opposite directions. And you can actually see this in the bridge. You'll notice how the bridge, the guardrail, has a curve in it because that end of the bridge on the other side is moving one way and this side of the bridge is moving another. And that's a good indication of what we call fault creep. We didn't have a big earthquake where the ground snapped and broke this bridge in half, but we can see how the land is slowly moving different directions. So once again, it's an example of fault creep. So here in Parkfield, California, where that fault creep is happening constantly, they've erected these two stone monuments here, one here and one back over here, which look like puzzle pieces that were originally together. And the distance between them represents how much this fault has slid or creeped over about the past 90 years.
The fault creep is the slow movement of the faults of the plates past one another, and they don't generally result in earthquakes. Now, we do have faults close to home. We have the Brevard Fault, which cuts through North Georgia. You see it runs right through metro Atlanta here. It's actually where the Chattahoochee River is flowing because the fault has a crack in it where the ground has been cracked. And that now makes a low point, and that's actually where the Chattahoochee River tends to run. Our fault here is an old fault. It's not very active. It's not moving very much anymore. So we don't have a lot of earthquake activity along this fault. Now, here's some other examples of fault creep. This is in Haywood, California. You can see the sidewalk is actually curved, where over the past 100, 150 years, one fault's going one way and one is the other. They studied these fault movements in Hayward, California, all the time because it can help us try to predict what's going to happen with earthquakes. These two curbs here, when they were installed, used to be put together, and now they're slowly moving apart. And all over town, you can see this where things that used to be lined up in a straight line are not together anymore. Now, if your house happens to be right across the fault, well, your house is not very flexible. The City Hall in Hayward, California was built on both sides of the fault. They didn't know any better when it was built. Well, now the building is being pulled apart. It has cracks in it. The building here, the City Hall, is actually been condemned. They can't use it anymore. It's closed down because it's not safe because the building is being pulled apart by that fault creep. There's also an aqueduct. We know California has a lot of these underground aqueducts and above ground aqueducts that are moving water around the state. Well, the aqueduct crosses the fault, and one side of the fault is moving one way and one's moving the other, and now their aqueduct tunnels and their aqueducts on the surface are being pulled apart. And when they drained the aqueduct, they went in and they looked at it, and they could kind of see here, notice these red dots don't line up with those red dots there. The water tunnel, the aqueduct, is being pulled apart, and that's obviously a problem. Ironically enough, University of California, Berkeley built their football stadium right across the fault line. Like, it cuts the stadium in half. This means half the stadium is moving one direction and the other half of the stadium is moving the other. Obviously, this structure doesn't bend very well. So now they have a bunch of cracks and gaps where the stadium doesn't fit together much anymore. So we have all this earthquake activity. How do we detect and measure the earthquakes? Well, earthquakes transfer energy by what's called seismic waves. A wave is a transmission of energy through a material, or in some cases through open space. But in this case, we're transmitting energy through rocks, through the ground when rocks snap and break and release energy. That is called a seismic wave. We measure it when those seismic waves push in the ground and it causes the ground to shake. Well, we can measure the amount of shaking. This is called a seismometer, or the printout that it gives, the piece of paper, is called a seismograph. You hear those terms interchangeably, but really, more correctly, the seismometer is the device and the seismograph is the piece of paper or the readout. And you've probably seen these in science fiction movies before, documentaries, whatever. And you've seen that they use these or read these to show how much the ground has shaken during an earthquake. Because the more the ground shakes, obviously, the bigger the earthquake. Well, here's how this works. Basically, we've got a roll of paper that rolls at over a certain time. And in its simplest sense, what we have here is a really heavy weight that is suspended. And it doesn't move very much because it has a lot of inertia. So when the ground shakes, my roll of paper moves back and forth. Well, my pen that is connected right there to the paper will then move back and forth. And obviously, the bigger the mark the pen makes, the more the ground was shaking. So we can see right here, that was my earthquake. Over here, the ground was not shaking. The pen stayed still. Over here, the ground was not shaking, so the pen stayed still. We can see how much the ground was shaking by how much the pen moves across that paper. Now, we have seismometers in Georgia. Georgia Tech especially has these seismometers placed all over the state to measure how much the ground shakes at a different location. Because remember, the ground is being shaken under the ground and it comes to the surface. So when you have the seismometer at the surface, you want one as close as possible to where that point was happening under the ground, and that can tell you where the earthquake was. So you can't have just one seismometer. You have to have a system of them, and we actually have them around the state here in Georgia. Now, how do we describe the size of the earthquake? We use this called the Richter scale. The Richter scale, you probably heard it on the news. You hear a number that says, oh, we had a 5.5 or a 7.2 magnitude earthquake. Now, the Richter scale was developed early on in science to try to describe the shaking of an earthquake in something that we could relate to. Most people weren't scientists, and they knew that when you exploded TNT or dynamite, had a really big explosion, it made the ground shake. Well, okay, sure. Let's relate earthquake shaking to how much TNT it would take to make the ground shake the same way. Now, the problem with this is, yeah, I get it. It's kind of easy to visualize, and a lot of people, especially back at the time, oh, we use TNT to make holes in the ground, cut through tunnels. We can visualize this. The problem is that the energy released by an earthquake dwarfs any kind of practical amount of TNT. You can see that we're talking about 6 tons of TNT. Nobody sets off 6 tons of TNT at one time. So even though the scale makes sense, it's really outdated and it's not used by scientists anymore. It's what you hear on the news. Here's a better scale to describe earthquakes. It's called the Mercalli intensity scale. And what this is it describes not the energy, but what kind of damage or what did you feel from the earthquake. This is very similar to that Fujita scale when we used to describe tornadoes. Remember, the Fujita scale didn't really have to do with the wind speed. It had to do more with how much damage does this tornado cause. And that's what the Mercalli intensity scale does. It describes how much shaking that you felt at a certain location. And it's different depending upon how close you are to the earthquake. And you can see high end, Mercalli scale 11, well, that means it was so much shaking that you could actually see the waves in the ground. Things got thrown into the air. If it was a Mercalli scale 1 or 2, well, nobody really felt it. It didn't shake the ground that much. There was an earthquake there, but it really didn't do a whole lot. This scale is becoming more and more in vogue. Now, you even start to hear it on the news because it's a much better descriptor of what did the earthquake do, as opposed to that Richter scale with, sure, we know a 5, 6, 7, 8. We know those are big earthquakes, but it doesn't give us a description really of practically what it meant to the people at that location. Before and after shocks, an earthquake can have a small release of energy before the rocks actually snap in total, and after the rocks snap in their biggest snap, they can have these little kind of rippling aftershocks. These are other releases of energy prior to or after earthquakes. Usually they're much smaller than the main quake. Aftershocks Foreshocks, they can be a couple hours, a couple days, they can be a couple weeks, either before or after that main breaking of the rocks. So now we're going to move into earthquakes number 2. And this is, well, how do earthquakes cause us harm? And what can we do to be safe from earthquakes? First of all, there are 4 main hazards from earthquakes. You see them here. The shaking. The shaking can cause damage. The shaking can kill you. Liquefaction, landslides, and tsunamis. We're going to look at all of these separately and talk about what they are and how do you keep yourself safe. First of all, the seismic shaking is just what it says it is. It's the physical shaking of the ground when the earthquake releases energy. The trick is with seismic shaking is the less sturdy the building you are in, the more likely it is to be damaged by shaking. Makes sense. If you're in what's called an unreinforced brick building, those are easily damaged by shaking. If you're on a place where the ground is really loose, especially if it's fill dirt, like you've brought in extra sand and soil, you're not on solid rock, well, that gets shaken and moved very easily during an earthquake, so you're going to have a lot more damage. And here's something we need to understand. This is what kills most people during an earthquake. It's when the building they are in comes down on top of them. So the shaking has an impact on the building you're in. If the building comes down on top of you, that's what kills you. Buildings made of brick shake apart very easily. Now that seems kind of backwards because, man, we like to assume that brick is a very sturdy material, and it is this way. You could pile a stack of bricks up without even any mortar in between them, 10, 12, 20 feet, and you could stand on top of the bricks and they won't fall over. Brick is very strong vertically or up and down. However, brick is not nearly so strong this way. You can knock over a brick wall with a hammer, because brick is not meant to have strength side to side. It's meant to have strength going up and down, which makes sense. That's why we could build really tall brick buildings. That's why it was used to build early skyscrapers, because the brick can be strong vertically. But if you go in a place where you have an earthquake, the side to side movement, bricks will come apart very easily. If you're in California or other earthquake prone areas, a lot of times you will be told, you will be informed that, hey, this is an unreinforced masonry building, which means brick or block. And you may not be safe inside of that. Even though it looks like a nice brick sturdy building, it will shake apart very easily in an earthquake. The same is true of concrete. Concrete does not flex. It does not bend. So when you get the side to side movement this way during an earthquake, concrete doesn't flex very well, which means it just snaps. So concrete, brick, block, not very safe. These are some older homes that were built probably in the 1910s, 20s maybe, but before our modern building codes and more modern building techniques, before we understood earthquake safety. This was San Francisco, where they even knew they had earthquakes. Ironically, this was built after the big earthquake in 1906. They built these buildings, and they were not built to be reinforced. And when the ground shook in the 1989 Loma Prieta earthquake, all of these older buildings just shook right apart and fell down. So if you live in these buildings, what should you do to be safe from earthquake? Get outside and get away from anything that can fall on top of you, because that's what kills you. So big, wide, open spaces are the best place to be during an earthquake.
So let's look at some earthquake safety steps they take here in Tokyo, Japan. They know they have earthquakes here, and they know that people live in these big, huge buildings that are going to be damaged during an earthquake. So they set aside these public lands, these parks, as a place where people can go and be out of the damage and destruction of an earthquake. And they plan for people to come here. Back there behind me is an emergency water storage facility, because if your water pipes get broken and you lose electricity, you can't pump the water, you got to have a place where people can come and get it. And they have these all over Tokyo, so that in the event of an earthquake, people can still get the things they need. In addition, they have a warehouse back there which stores safety materials, medicines, food, etc. So they really plan for earthquakes here in Japan, because they know they've got them, and when they do get them, they can be bad.
have signs all over Tokyo pointing you in the direction of places where you can be safe from an earthquake, especially for tourists. Because if you're a tourist there, you're not used to living with earthquakes. You don't know what to do in the case of an earthquake. And they set aside this area for you to go, generally out in the open, big public parks, because they know you can be safe. Now, what about our homes? The houses we live in are actually much safer in earthquakes because they're made of wood, and wood is nailed together. Wood can bend and flex, has a lot more give and take to it than concrete or brick. So if your house gets shaken back and forth, all of the wood will wiggle back and forth, and it's hard for your wooden frame house to come down on top of you. And even inside of your house, if you're inside of a wood built stick house and you're in California, where should you go in your house? Go stand under the door. We say the same thing with tornadoes because your doorway has this larger piece of wood over the top of it to help keep the door straight so that it always opens and closes smoothly. That's called a header. Well, you see, it's bigger and thicker, so it's going to be a lot more rigid and it's going to be a lot more less likely to come down on top of you in an earthquake or in a tornado. This is what kills you. It's not just the house, it's the stuff inside the house. If you have heavy things inside the house, like a bookshelf, in the old days, our big TVs that were so heavy, your dining room cabinet, other large piece of furniture like a refrigerator, that stuff falls on top of you and that's what kills you in an earthquake. So what can we do to minimize the likelihood that you're killed or hurt in an earthquake? Well, places that have earthquakes, they actually sell these things. It's called a quake hold or the seismo latch or the anti-tip fastening system where they attach their large items to the wall so that when the building shakes, stuff doesn't fall over. And more than just providing you safety, think about your big screen TV. Your big screen TVs now are very light, and they would actually get knocked off the entertainment center or even knocked off the wall in a very small earthquake. Well, they're expensive. So you attach these things so if you have a small earthquake, you don't lose your TV.
So something else that can be done to help make a building a little bit more earthquake safe, especially when it's a big tall building that can waver back and forth a lot and fall down, is you put in this extra metal bracing like you see here. And that gives it a little bit more strength, and the metal actually can flex a little bit more and wiggle a little bit more than the concrete of the building. So this is done in places like here in Japan where earthquakes are a real serious concern, especially in big tall buildings.
So you see this engineering all over Japan, New Zealand, places where they have a lot of earthquakes, this extra metal, either when they build the building, or in this case, this was an old school that was probably built in the 1950s before they really understood earthquake safety. And they went back and they put in extra metal bracing so that when they do have an earthquake, the building can flex and not collapse. See it here. Sometimes you'll see these hinges in buildings. You'll see these metal sections, and it looks like a hinge, and that allows the building to flex more in an earthquake and therefore be less likely to collapse. It's not just in Japan. You see, this is in Oakland, California, where they built the building to have some metal framework so it can bend during an earthquake, because they have earthquakes in California. You can see it in the parking garages. A lot of metal, lots of ability to flex and bend. Now, what if you have an older building? You can't go back and rebuild it. However, you can add metal. And that's what they've done right here. These are some metal pilings that they put on the exterior of a brick building so that when the earthquake happens side to side, the metal will help keep the brick a little bit more solid. Same thing here. These look kind of like landslide anchors, and they're very similar. These little pins that you put in the brick to help hold the brick together in the event of an earthquake. This was an old museum in Hiroshima, Japan. It was built probably in the 50s, and at the time it was under renovation because they were going to earthquake-proof the building. It was built before modern earthquake safety standards were clearly understood. So in places like Japan, they're going back and rebuilding the buildings to make them more safe. Now, liquefaction. Liquefaction is another real serious concern. Remember that energy from the earthquake is coming to the surface. We know that down here, there's a bunch of water. Well, if there's enough of a force pushing up, the water can come to the surface. Think about this as like a temporary natural spring because the water is getting pushed to the surface, and now we wind up with a bunch of extra water on the surface. The ground can become liquefied. Well, if your house isn't on top of ground that becomes liquefied, it's not strong enough to hold up the house. The house can actually tip over, it can collapse. And you see this here in this picture. This was in Japan. These were buildings that were made to be earthquake proof. You see, they didn't fall apart, but the ground under which the building was built liquefied and the building fell over. Still stayed in one piece. It was a nice, strong building, didn't fall apart. So the question is, can this kill you? Answer is yes and no. The building didn't fall down on top of you, but if you were inside this building right here, your refrigerator comes across the kitchen and pins you up against the wall and kills you. So another reason why in places like this where they have a lot of earthquakes, you want to take steps to attach your stuff to the walls so that it doesn't fall on you and kill you. Another example is in San Francisco during one of the earthquakes. See, the buildings were intact. They didn't get shaken apart. The ground became gooey or liquefied, and the buildings slumped over. San Francisco has a terrible time with this because San Francisco needed more land. And what they did was they went out here and they built on these wetlands. They filled in a lot of the wetlands with extra soft materials, soils and dirts, and sometimes even trash. Well, there's already a lot of water in the ground. So that means when the earthquake happens, these areas around San Francisco are very susceptible to liquefaction and damage from that. It's not just the buildings, it's your power lines and your water lines and your gas lines. If the water is coming to the surface, it's going to push on your gas lines. It's going to push on your water lines, and those things will break. So you lose gas, you lose water, you have fires, and that's also a way you can get damaged during an earthquake. You can see it here in this road. This was caused by liquefaction because we're talking about a lot of water and a lot of push from an earthquake can do this kind of damage. Landslides and mud flows. We talked about this with erosion. We know what kind of damage we can get here. Well, an earthquake can shake the hills and kind of get the landslides going. Something like this here. These houses were fine during the earthquake, but they got taken out by the landslide that came down from the shaking of the ground from the quake. Now, a tsunami is a very uniquely earthquake associated hazard. This happens when an earthquake happens under the ocean floor. The earthquake pushes the water up and makes a wave. And then when the wave reaches the shallow water near the shore where the people live, it pushes a bunch of water into a huge wave that comes on the shore. And that's what a tsunami is. It's a large wave caused by an earthquake pushing the seawater. The word tsunami is a Japanese term. They have a lot of earthquakes there, which means harbor wave, because that's where you would see its effects. It looks something like this. Earthquake happens, ground gets pushed up, makes a big wave, wave comes to shore. If you're standing in the way, something like this. Now the trick is, out in the middle of the ocean, tsunamis don't look so impressive. You're on a boat in the middle of the ocean over the tsunami, you might not notice it's a very large wave. But when that wave reaches the shore, all of the water piles up and it becomes a lot more damaging. Now, how far can these things travel? They can go thousands of miles because water transmits the energy so easily. So if you're nowhere near the earthquake, you can feel the effects from the tsunami. This was in 1960. They had a really bad earthquake in Chile. And the tsunami actually hit the state of Hawaii thousands of miles away. Those poor people in Hawaii, they didn't even know there had been an earthquake. They just all of a sudden had the tsunami come ashore, and it was devastating in the town of Hilo. It bent parking meters over, and they were 6,000 miles away from the earthquake. So, as long as we're on this subject, how big can they get? Well, they can get up to 100 feet tall. That's a really extreme, but most are only about 10 foot. But even a 10-foot high wall of water is really, really powerful. How fast do they travel? Well, about 500 miles per hour, which means they can go across the entire Pacific Ocean in a day. The town of Hilo, Hawaii has been hit by tsunamis multiple times because they sit out there in the middle of that Pacific Ocean and they're ringed by all kinds of areas that have a lot of earthquakes. There's a palm tree there in a park in Hilo where they have marked the height levels of the different tsunamis. You can see 1957, oh, it was 8 feet tall. That's a lot of water. That came ashore and hit your house. An 8-foot wall of water would knock your house over. 12 feet, 15 feet, and in, I think, 46, 26-foot tall wall of water. That is just devastating. And this is different than the storm surge from a hurricane. We've seen how bad that can be. This is all of it coming ashore one time, wall of water going really fast. This here is not special effects from a movie. This is the actual footage of a tsunami coming over the seawall that was built to protect from tsunamis. This was in Japan in 2011. So you can see this is not just like a little water comes in, a little bit more. No, it all comes in at once and is very powerful and very damaging. This is what it did to this particular city. Think about this boat here. It wound up on top of a building. That's how big and how powerful a tsunami can be. This is Indonesia in 2004. This is the before and after pictures, and you can see what devastation it caused. It even uprooted trees. And you know trees are rooted in the ground. Trees are hard to knock over. And a tsunami can be so powerful, it could just be incredibly devastating. So what can you do? Well, in places where you have tsunamis, the number one thing you want to do is get to high ground. Get high enough inland and up in elevation that you are above the highest water level. We saw in Hilo, that could be 27 feet, which you don't have to go that far inland. And what they'll have is a siren. Like we have tornado sirens. They have tsunami sirens that go off, and people hear that going off and like, oh, okay, there was an earthquake somewhere, not even necessarily here, and I need to move inland. They will have signs in places like Hawaii that tell you where you are safe from a tsunami. Oh, I'm going down to my hotel. It's near the beach. Oh, I'm in an area where when that siren goes off, I need to leave this area. Now, out in the middle of the ocean, they're putting out these buoys, and they're tied to the ocean floor. And what these buoys can do is measure when the buoy goes up and down very radically. Oh, we've had an earthquake. The water is moving. They send a satellite signal to satellite, and they send a warning system out. And this is helping people at least know that a tsunami is coming, giving you more of a heads up before the tsunami comes ashore. And then you get a text alert. Hey, we got a tsunami alarm. If you're in this area, go to higher ground. In Hilo, they have built a huge breakwater to help slow down the water in the event of a tsunami. We know how breakwaters work. They make water go slower, and it works the same here for a tsunami.
So here in Japan, specifically Tokyo, where you're right along that edge of the Pacific Plate and earthquakes are a real serious concern, you have to do things to help protect yourself from damage from an earthquake. And one of the major causes of damage, especially if you're on the coast, is a tsunami. And here we've got a river, and if an earthquake happens and pushes a bunch of extra water up this river, it's going to flood and then knock down homes and people in this area here. So what they've done in Tokyo is they have lined their rivers with these high walls so that when water from tsunami gets pushed up the river, it's not able to go over the wall and therefore cause damage. Now sometimes you're limited as to where and how much wall you can build. So in this case, we've got another little offshoot from the river, and it has these huge doors that would come down and cut off water from being able to go up this little river in the event of a tsunami coming after an earthquake.
So when and where are these earthquakes going to happen? Well, first of all, earthquake time and season. There is no such thing as an earthquake season or time of day. They can happen any time of the day during any time of the year. Now, they don't happen everywhere, but they're not dependent on things that happen on the surface. So how many earthquakes are we talking about here? Well, we get about 500,000 a year in the world. That's in the world. So Today, there is an earthquake that has happened probably in the time of this class period. How big was it? Depends. So how many happened in the United States? 20,000. Now, you've heard about earthquakes on the news, probably haven't heard about one recently because most of these earthquakes are small. Yes, they are rocks that are being snapped and releasing energy, but they're not big enough to cause damage, so you don't hear about it. So where do these things happen? If you'll notice this picture here, all these black dots seem to match up another shape that we already saw. These black dots are showing us where earthquakes occur. And that map matches our plate map because earthquakes tend to happen at plate boundaries. This is where the plates are either sliding past one another or moving up underneath one another. That's the place where the rocks are being bent and squeezed and they eventually snap. So earthquakes tend to happen at plate boundaries. They can happen away from plate boundaries because sometimes those plate boundaries are deep under the ground and go away from the actual boundary, but this is the general place where you get more earthquakes. Now, in the United States, that means we get a lot more earthquakes along the West Coast because that's where that plate boundary is. In the Atlantic, the plate boundary is way out here in the mid-Atlantic ridge. And that type of plate boundary out there, which is a divergent boundary, doesn't tend to make earthquakes. But on the West Coast, where we get these plates moving back and forth, like this. Well, they're rubbing back and forth. They catch those rocks. The rocks snap and they break, release energy. We get a lot more earthquakes in the West. Now, however, the number one earthquake state in the USA is not California. It is actually Alaska. So why do we hear so much about California with earthquakes? Well, the thing is, in California, there's a lot more people in California. So when an earthquake happens in California, millions of people feel it. Millions of people call the news station or the newspapers, and it gets reported. If they have a big earthquake, it causes damage, and the news crews run out there and they take pictures, and it gets broadcast worldwide. Alaska is very remote with very few people. So an earthquake happens, let's say, out here. And there's very few people out there. So even if it was a really big earthquake, it doesn't cause a lot of damage, and therefore it's not as much newsworthy. There are earthquakes, big earthquakes that happen in Alaska, and practically nobody ever feels them, much less has any damage from them. Now, do we have earthquakes here in Georgia? The short answer is yes. The largest earthquake ever in Georgia was in 1914. It was a magnitude 4.5, which is to say it wasn't a very big earthquake. Might have caused a little bit of damage, some cracks in some homes. People certainly felt it, but they don't cause a whole lot of damage. So we've had less than 50 earthquakes of 2.5 or greater, and that's a small earthquake. And you see this map here shows all earthquakes of 2.5 or greater since 1900. So our conclusion about Georgia earthquakes is, yeah, we have them here, but they don't happen very often, and they're often very small. The strongest earthquake ever in the United States happened in 1964, and it was a magnitude 9.2, which is to say it was a beast of an earthquake. It was incredibly incredible. It's the second most powerful earthquake ever in recorded history. Happened over here in Alaska. Now, one thing about this earthquake, though, they got lucky. Happened on Good Friday, which was a holiday. So where were most people at on a holiday? Well, they were in their house, which is made of wood. So there was less likely a chance that you were going to be hurt or damaged. Had this happened on a work day, when kids were in school, people were in downtown office buildings made of brick or stone, there would have been a lot more deaths. And it also happened, I believe, at about 5 p.m., meaning that everybody was awake and the ground started shaking and people had time to get outside. If an earthquake happens at 2 in the morning and it wakes you up, you might not have time to get outside and be safe before your house or your building or something falls on you and kills you. Now, the strongest earthquake ever in history happened in Chile in 1960, and that was a magnitude 9.5, which was incredibly powerful. And this is the one that sent the 27-foot high tsunami of water that hit Hilo, Hawaii, and actually caused deaths there. So our deadliest quakes in the world. I want you to look at here. We got China, Haiti, China, Indonesia, Japan, Turkmenistan. You notice we don't have a location here in the United States because we don't have as nearly often an occurrence of earthquakes, and we don't have as powerful of earthquakes generally in the United States. The deadliest one in the United States was San Francisco in 1906, and you notice 2,000 people compared to what the numbers we just saw. Not a lot of people die from earthquakes in the United States. However, in 2010, we had one in Haiti, which is close to us, that killed thousands of people. The question is, why? Well, if you live someplace where you don't have very good building codes, and you live in kind of ramshackle housing, and you live on a very steep slope, and the ground starts to shake, your building comes down on top of you, and that's what kills you. So our conclusion about earthquake deaths is fewer people now die from earthquakes because we can get the word out, and we have better earthquake safety. People understand, people are more educated. But more people are going to die in poorer countries because they don't have that advantage, and they tend to live in substandard housing, which comes down on top of them, and that's what kills them. So that's the end of the presentation. You can bring me your summary sheet completed for a done stamp at this time.